So now this very how are you? Good. Oh, that's right. All right. Hello, everyone. Today we're very fortunate to have Anna Meg with us. Anna,
recording in progress.
With Aaron.
And she managed to get away from the fourth round. She turned to phone sensor and using contact. Trying to understand like that matter. She did a PhD at Cambridge, and then a clinical profile at Cambridge before moving to NYU.
Yeah. Cool. Thank you very much for having me. It's really fantastic to be here. So it's 2026, and we have an abundance of evidence for new physics beyond the standard model and for dark matter. Yet, despite a pretty relentless experimental campaign, which has encompassed all manner of direct detection, indirect detection, collider searches, we're still no closer to really finding out what this dark matter is. And to me, this is one of the kind of biggest, like, I want to say failures of science, the fact that 85% of matter in the universe, we know it's there, but we literally have no idea what it is. And to kind of encapsulate the state of our ignorance, and this is not going to let me, is that going to let me now? Yeah. Kind of, I think this plot, which you've probably all seen 1,000,000,001 times, really encapsulates the state of our ignorance, which says, under the very minimal assumption that dark matter is a single particle, a single new species, it could really be anything from something which is like a 10 to the minus 22 electron volt boson, all the way up to something like extremely heavy above the Planck scale, primordial black holes, matches, etc. And given this extremely very broad landscape, the fact that we haven't seen anything when, to be fair, most of our kind of searches have been largely concentrated around this kind of GeV region, the WIMP. And of course, the WIMP is extremely well motivated. You're all familiar with the WIMP miracle. However, we've yet to see anything. And that, to me, really kind of motivates a kind of more broad exploration of this landscape. Now, one of the reasons why WIMPs have been so kind of historically so well probed is, yes, of course, their theoretical motivation, but B, partly because the technology that we needed to probe WIMPs back in the sort of 80s and 90s, it was seen as kind of feasible. Whereas some of these other regions have the technology required to kind of really explore them wasn't really in place about 30 or 40 years ago. And this is really kind of an example of how kind of the technology that's available has been really driving what we tend to explore in terms of dark matter. Now, the WIMPs are obviously a very well motivated thing. And perhaps maybe the reason that we haven't seen WIMPs, perhaps they're just sitting at energy scales that are above what we've been able to probe and experiment. But kind of an alternative and possibility, which has become more and more kind of tantalizing and more exciting to think about, I think, is that instead of being an inaccessible energy scale, what if dark matter is actually just hidden behind an extremely feeble Hubble coupling to the standard model? So it exists at energy scales that we're already probing, but its couplings to the standard model are extremely feeble that we haven't been able to see it. And this is where this kind of ultralight regime comes in. And by ultralight, I mean dark matter, which is below an electron volt. And this means that it has very, very different properties and phenomenology to its heavier WIMP-like cousins. So to kind of just give you a bit more of an overview of what I mean about ultralight dark matter, I just mean a sub-electron volt candidate for dark matter. And it turns out that because your particle species is so light, if you want this to saturate the dark matter abundance, it's going to have a very, very high number density. So your phase space density is going to be significantly above 1. And as a result, all the kind of quantum effects of this get like washed out. And you can just treat this as a classical wave. And of course, a classical wave means that it's behaving very, very differently to WIMPs. So WIMPs, when you do a typical WIMP search, we're looking for like an impulse resulting from a particle-particle collision. Whereas here we've got something which is behaving like a coherent oscillating background wave. And this means that the detection principles that you need to be able to kind of search for this are going to be very different. So instead of looking for impulses, you're going to be looking for something which is really exploiting the coherence of this field over long timescales. So the second thing is, why does this behave as a wave? Why can we think of this as an oscillating phenomena? So the theory behind this is really quite simple. If you take any free scalar particle, so just like an m squared phi squared term, if you imagine that early in the universe, this field is just displaced from its minimum by some kind of field excursion, so phi naught. If you then just let this thing evolve over time, what you find is that it ends up oscillating about its minimum, so at late times. And that's exactly what ultralight dark matter is. You just have a field in the universe, and at late times, you find this thing is oscillating, so it ends up looking like a cos term. And this means that it gives rise to a number of very distinct phenomenology, which I'll kind of go along with now. This mechanism is just known as vacuum misalignment. It's kind of what people generally think of when they think about axion production, but it works whether it's a scalar or a pseudoscalar. Okay, fantastic. So we've talked about how this thing might be produced. The next question is, what kind of signatures could ultralight dark matter have? Well, we've already said that it's an oscillating wave. So that means the signatures you're going to be looking for are going to be typically oscillatory in nature. And the exact way that we might observe this thing depends on how it couples to the standard model. And the way that dark matter is going to couple to the standard model can be kind of categorized very compactly and very distinctly via the spin. So you can either think about your dark matter being a scalar, so a spin zero particle. And of course, scalars can come in two types. They can come in scalars, which couple, assuming that CP is conserved, they're just going to couple to kind of mass terms. And we'll talk a little bit more about that in a second. And there's, an abundance of dark matter candidates that fall into this category, including moduli, dilatomes from string theory, the relaxion, which solves the electroweak hierarchy problem, Higgs portal dark matter. Then we've also got the kind of perhaps more famous cousin of pseudoscalars. So these are things like axions or axion-like particles. So these things that couple with CP odd couplings to the standard model. And then, of course, you don't just have spin zero, you can also have spin one candidates. So these are vector bosons. People typically talk about dark photons, which are things which kind of couple to the standard model just via kinetic mixing to the standard model photon. But you can also have a spin one boson, which is like the gauge boson of a new U1 symmetry, for example, B minus L. So in this case, you have a direct gauge coupling to the standard model. And each of these different classes give rise to a very distinct static phenomenology. And I barely scratched the surface of what we have here, but broadly speaking, if you've got scalar spin zero dark matter, that's going to induce a temporal variation in fundamental constants. And in turn, that's going to cause anything that depends on fundamental constants to oscillate in time. So things like energy scales, length scales. If you've got an axion, because it's a pseudo-scalar coupling, this generally causes like spins to precess. And this is what they look for in like Casper and experiments like that. And then, of course, we've got spin one vectors. And again, it depends on the type. So if it's a dark photon, again, you can kind of get spin effects. If it's B minus L, what you actually get is oscillatory forces acting on macroscopic objects. So these couplings, the way that something couples to the standard model really tells us how we might be able to think about probing it in the lab. I should probably actually mention also, of course, axions, you're all familiar with the kind of electromagnetic coupling and axion going into photons, and that's what they look for in ADMX. But I'm focusing more here on the signature that you might see with like a collection of atoms or some kind of quantum sensor that you're building in the lab. But basically, you can see that there's a very wide range of phenomenology that you can get, just even when you're considering stuff that's below the electron volt scale. So I'm going to talk about various different ways that we might be able to probe these things. And I really want to just emphasize that these things couple to the standard model incredibly feebly. And it was previously thought, you may well have heard this story, like back when the axion was kind of, people came up with the axion, they originally thought, well, there's no way that we'd ever be able to probe this thing. And people actually called it the invisible axion. And it's only really been, in the last sort of 10, 20 years that the technology has become available to be able to probe these. And we now have, things like ADMX and all these experiments which are claiming they can actually get to the QCD axion line. And it's really thanks to kind of transformative advances that we've seen in quantum sensing technologies that this whole, if I go back to my plot of the landscape of dark matter, this whole kind of region has become available. And to me, that's a really, really exciting time that actually we've gone from thinking, okay, well, we can only really probe, a subset, but now we've got this much broader landscape that we're able to probe. And to me, that's a really, really exciting thing. So quantum sensing technology, of course, is just one way that we might be able to probe dark matter. I'm not saying it's the answer, but I think it's something that's certainly very exciting. And I think it's, you know, it's taken us 30, 40 years to kind of even just, you know, begin to explore in the WIMP. And the fact that we've now got this whole kind of tantalizing set of opportunities to probe a wider case, I think really motivates us exploring it as widely as possible. And I'll really just be scratching the surface here today. There are, you know, just a few ideas that I'll be talking about. But my hope is that it will get you excited about what people are able to do in the lab. I know there may be some experimentalists here, and I'm absolutely in awe of what you guys are doing. So maybe you will have ideas. But the idea that I'd like to get across this talk is that there's really kind of the rate of progress that's going on in, you know, people in labs building these kind of quantum sensors. It's really opening up a whole load of opportunities, and we need people getting together and talking about, you know, what we can do. As a theorist, you know, I don't really know quite what's going on in the lab. As perhaps as an experimentalist, you might not know all the dark matter signatures, but we need to get people together talking about this sort of thing, and hopefully we might be able to come up with some new ideas for what, you know, being able to capitalize on these advancements in the lab and using them to actually search for dark matter. And that's something which I'm really, really excited about. So I'm going to begin by talking about spin zeros. This is the scalar dark matter. So for those of you that are theoretically or mathematically minded, we can describe this by the following Lagrangian here. So basically all you have is you have some new scalar field, which is dark matter, and it couples to basically all scalar terms in your Lagrangian. So you have your normal you know, electromagnetic field strength tensors, but you have now a coupling dE. So this is basically just saying that your dark matter is talking to photons. Dark matter could also talk to gluons, but it also couples to mass terms, as in mass of the electron and mass of the quarks as well. And this thing, remember, goes as like cos, it's like a wave. So as a result, if you had like your normal standard model Lagrangian, you'd have like an ME bar E, which is just your mass term. Now we've got this extra thing here, which depends on phi. So what you'll actually see is that the effective mass that you measure now has an extra term. So you have your raw mass, then you've got this extra effective mass coming from the coupling to dark matter. And because this is oscillating in time, it means that your mass is going to oscillate in time. So, I mean, I will say it's not like physically the mass is measuring, but what appears as the mass, what you measure as the mass in your experiment is going to oscillate in time. And the fine structure constant and the strong coupling constant are going to do the same thing. So it's quite a bizarre thing, the fact that, you know, nature is appearing to oscillate in time. But of course, every physical observable energy scale, length scale is going to inherit this oscillation. If your fundamental constants are oscillating, the energy scales and length scales that depend on these are also going to oscillate. And this gives us a number of opportunities to be able to probe these things in the lab. So to start with, I'm going to introduce you to atomic clocks. So an atomic clock is basically just a two-level system. You've got two stable energy levels. And it turns out that the energy transitions in clocks, you can always write like the omega, the frequency, as a function of fundamental constants. So I'm going to use X just to denote a generic fundamental constant, which could be fine structure constant, mass of the electron, whatever. And it turns out each clock transition you have, you can write it as a function of these constants. And you can capture like the dependence of each transition on the constant by this enhancement factor, which is basically just a derivative. So it's just saying, if I change my fundamental constant, how does the energy of my transition change? And it turns out that every different transition energy has a slightly different dependence on these fundamental constants. So now, if you take two different transitions, omega 1 and omega 2, so this could be either two different clocks, or it could be two transitions within the same clock. And if you take the ratio of how these things, you'll see that it depends on how the fundamental constants change in time. So let's say you've got dark matter that couples to a photon, so it's changing your fine structure constant. So let's say you've got delta alpha over alpha is some small number, that's just the dark matter. You can see that the ratio of your fundamental constants is going to depend on the difference between these enhancement factors. So if you want to get really strong, well, if you want to get the best sensitivity to dark matter, what you need to do is pick two different clocks which have different K. So the bigger this difference in K is, the greater sensitivity that you're going to get. And it turns out that different types of clocks have different sensitivity to different fundamental constants. So the kind of best like precision timekeeping clocks that we have are optical transitions. So they're just transitions that are in the optical regime. These give you sensitivity to alpha, they give you sensitivity to the electron mass, and their typical K values are about 1. And I should say that the reason they're sensitive to these things are because it's an electron transition. So it depends obviously on the electron mass fine structure constant. If you have a hyperfine clock, so that's a clock that's in the microwave region rather than the optical region, these guys, they do actually have some weak sensitivity to gluons and quark masses as well. So therefore, if you compare an optical clock and a hyperfine clock, you can actually get some weak coupling to these things. So that allows you to test new physics dark matter that couples to quarks and gluons. And again, your difference in K is always going to be 1 in this case. So this is what you can do with an atomic clock. However, there's been a revolution in recent years. You may well have heard about this. I'm hugely excited about this. Recently, people discovered thorium-229, which is a nucleus. And it turns out this nucleus has an excited isomer, and that isomer is stable. Now, not only is it stable, but the energy difference between your ground and your excited state is 8.3 electron volts. And this really is quite a miracle. So typical nuclear transitions are like MEV. And this is actually the one place, as a theorist, the one place where kind of fine tuning is actually saving or being beneficial to us. So what you actually have here is like the energy scales for this thing are on the MEV level, but you have a fine-tuned cancellation between the strong coupling, the contribution to this energy from the strong force and the electroweak force, and they actually cancel out, and they cancel out to give a very small energy gap. And the reason why this is exciting is we have lasers that can operate in this regime. This is just like the very kind of high optical, they call it VUV, like it's a UV laser. So we actually have lasers that can operate at this energy level, whereas we don't have lasers that can operate at MEV energy. So typical nuclear transitions, you wouldn't be able to excite. We found one transition that you could excite, and it's thorium-229. And people get very, very, very excited about this because this gives us the opportunity of being able to build a nuclear clock. And you may well have heard there's been a lot of kind of noise about this recently. So why are people excited about a nuclear clock? Well, to start with, being able to excite a nucleus is in itself very, very exciting. But it actually turns out it has a lot of advantages over a typical optical clock. So to start with, you're now exciting a nucleus rather than an electron. And this means that the electrons are kind of shielding your nucleus. And this means that the transition is very insensitive to external perturbation. So things like if you've got some stray B field in your lab or anything like that, which is obviously a big advantage. If you're an atomic clock scientist, they get very, very concerned about kind of being able to control all the stray fields in their lab. So this is very, very beneficial. But the key reason why people are excited, at least from a fundamental physics perspective, is that this nuclear transition is extremely sensitive to the variation of fundamental constants. And again, this is all coming back down to the fact that you've got this finely tuned cancellation. That means that if you change a fundamental constant by a little bit, it's like you basically get this fine-tuned cancellation between different contributions, but you end up having a large sensitivity. So if I go back to comparing my typical optical clock, remember I told you these K factors, these enhancement factors were like K is order 1. For a nuclear clock, you can see that the K factor, the enhancement factor, is 10 to the 4 or 10 to the 5, depending on whether you're coupling to photons or whether you're coupling to gluons. So again, for an atomic clock, it's order 1 for photons, but an actual atomic clock, not atomic microwave, it's like 10 to the minus 5 for gluons and quarks. And the reason for that is because the only dependence on optical clocks on quarks and gluons is coming from like ME over MP, so the mass of the electron compared to the mass of the proton, which of course is suppressed by a factor of like 10 to the minus 5. So this is hugely, hugely exciting because if you've got your clock and you're saying, okay, my clock is sensitive to fundamental constants, if you could now build a nuclear clock, your sensitivity has gone up by 4 orders of 5 orders of magnitude. Now, I don't know about you, but when I hear someone say, oh, I've built this new experiment, I can get 1 order of magnitude improvement or like half an order of magnitude, I'm like, yes, I get really excited. This is talking about 4 orders of magnitude in one go, which is really, really quite extraordinary. So at this point, you're probably thinking, well, come on, Hannah, what is the catch? Well, the catch is that we haven't actually built this nuclear clock yet, but the rate of progress is quite extraordinary. So when I started thinking about this like a couple of years ago, and I was at CERN at the time when they were, so at CERN, they're actually looking at producing these thorium from radioactive decays. At the time, they knew there was a transition there, but they didn't know the precise energy. So if you want to have a clock, you need to be able to have your laser extremely, like it's a very weak transition, right? So you need a lot of laser power exactly on that transition. And they knew like it was roughly about 8, but they couldn't really tell you quite what it was. And that meant they couldn't get enough, they couldn't concentrate the laser power enough to actually excite this. So they'd seen it de-excite, but they hadn't been able to radiatively excite it. And then I was talking to someone there at the time, and they were like, yeah, you know, maybe within like 5 years, we'll be able to do it. We'll like, you know, we'll have it. But within like 5 months, they've been able to not only radiatively excite it, but then some guys, Junyi at Gila, he put a frequency comb on it, and they've now got the relative precision down to like 10 to the minus 10. So they can excite this thing, and they can already, you know, they already know much more, you know, precisely what the frequency is. That doesn't mean they've got an operational clock. I mean, this thing doesn't have the you know, the stability that it needs to be a leading timekeeper at the moment, but the rate of progress is really quite extraordinary. And as a theorist, this is something to me which is really, really exciting. You know, I talk to people that are like working on FCC or muon colliders and things like that, and you say, well, you know, when's the next, you know, what sort of time scale are you looking at? Oh, well, maybe by 2070 we'll have like, you know, the next collider. I'm like, well, great, but you know, I hope I'm still doing physics for, you know, 2070, but you know, who knows what's going to happen. But these guys, you know, you talk to the experimentalists in the lab, and I say, well, you know, what's the chance of you doing it this or doing that? And I'm like, oh, it's going to take me ages. And I'm like, well, how long is ages? And they're like, well, you know, maybe 2 years, 3 years. That's nothing, you know. So I think, again, with quantum sensing technology, you really have the opportunity to be able to drive it. And I think as a theorist, that's very, very exciting, because the people in the labs thinking about these things, they're not necessarily thinking about it from a fundamental physics perspective. They're thinking, well, you know, what can I do in the lab? And then as a theorist, you can go to them and say, well, you know, if you do this, or if you could do this, you would actually get really good sensitivity to dark matter. And I think being able to motivate things in that way is very powerful, but it's also very exciting to actually feel that you're able to kind of influence development. So if you could build a nuclear clock, and as I said, the technology is not quite there yet, you would be able, if you could do this frequency comparison, so instead of comparing 2 different atomic clocks, if you could compare a nuclear clock and an atomic clock, remember, because your K factor for the nuclear clock is 10 to the 4, your K factor for the atomic clock is like 1, so you've now got a 10 to the 4 difference. You would literally get a 10 to the 4 enhancement over what we currently get with atomic clocks, which is amazing. And I should also say, in the last, I think like 2 or 3 days ago, there was a paper out, and as I said, you know, they haven't built an operational clock. What they have been able to do is do spectroscopy on this nuclear line, and already by analyzing the line shape of this line, they've already been able to get bounds on dark matter between, I think, about 10 to the minus 19 electron volts. They've already beaten what people could do with atomic clocks. So this is not even doing a frequency comparison, it's just looking at like analyzing a line shape. They've already beaten by about an order of magnitude, I think. So you should look up this paper. It came out literally a couple of days ago. It's on the archive. And it's really quite extraordinary to think that, you know, the nuclear clock really is paving the way to be able to probe these laws of dark matter in the future. Okay, so it turns out that's not all you can do with atoms. So yes, you can build a clock, but you can do something which I think is also really cool, which is atom interferometry. So atom interferometry, again, if you're a terrible theorist like me, you probably struggled in undergraduate labs doing like Mach-Zehnder interferometry. With light, this works exactly the same way, but instead of like diverting the path of light, you're diverting the path of atoms. So I'll briefly go through what this is, because I know I always used to sit in talks and people would talk about atom interferometry and I'd never quite know what it was. So in case of anyone in the audience that maybe hasn't thought about this, like this is what an atom interferometer is. So basically you start off with your clock, and your clock is like 2-level system. If you ever shine something that's resonant with that transition, it turns out the probability of being in the ground and excited state oscillates. This is a Rabi oscillation. So if you start in the ground state, you shine a light for pi seconds in terms of this Rabi frequency, you get 100% transition. And likewise, if you start in the excited, you can go back to the ground. And this gives us a way of being able to kind of manipulate it. So if instead of shining it for pi seconds, if I just shine it for pi over 2 seconds, what I get is if I start in the ground state, I've driven my system into a superposition of your ground and your excited state. So this allows you to kind of basically be like a beam splitter in a typical atom typical interferometer. You can do the same thing if you shine it for pi, then again you transition from the ground to the excited. So this allows us to build an atom interferometer. So you start with something in your ground state. What you then do is you apply your pi over 2. So I've now got a ground state and I've got an excited state. Now the excited state has absorbed a photon, so it's got higher momentum. So these things are going to separate in space if you let them propagate. So I'm going to let this thing evolve for some long time t. And after a long time t, I'm going to apply my beam splitter pulse, which is going to, my mirror pulse, which is going to flip them. So the thing that did have extra momentum has now got less momentum, and the thing that didn't have momentum has now got momentum. So they're going to come back together in space, and I'm going to recombine them. And you all know from quantum mechanics that the rate of phase accumulation goes as the energy of your state. So if you've got something in a higher energy state, it's going to accumulate phase quicker than the ground state. So as you're letting these things propagate, this thing is going to accumulate phase relative to this thing. And it turns out if you then work out the probability of being in the ground and the excited state at the end of your system, the probability is just going to depend on the phase difference of stuff that's gone along this path and the phase difference of stuff that's gone along that path. Okay, all with me so far? Yep. So this means if you take the ratio of these things, or like the sum and the difference, you can actually extract the phase difference. So what an atom interferometer does is it measures the phase difference between the atom that's gone along this path and the atom that's gone along this path. Now, because this is symmetric, this diagram is symmetric, if there was no new physics and you were in flat space, no gravity, you expect the phase difference to cancel out exactly, right? But if you've got something that's accelerating, then the phase difference will depend on your acceleration. So you can use this thing as an accelerometer. But more excitingly, if you've got some kind of new physics effect, so let's say you've got your ultralight dark matter, and your ultralight dark matter is oscillating your energy levels, you're then going to get a phase difference that depends on the dark matter oscillation, okay? So this means your phase difference is going to tell you how dark matter is oscillating. Also, people use this for gravitational waves, because if you've got gravitation, I'll tell you how to do it with gravitational waves as well, but gravitational waves basically just changes the time. So yeah, so it's not as simple as I just showed you. In practice, if you're building an atom interferometer, what you actually do, there's two subtleties. So in practice, you have two of them separated by a long baseline. And the reason you do that is every time you shoot a laser at an atom, you're going to impart some noise from the laser. So if you've got two of them and you're shooting them with the same lasers, the noise will cancel out. So that's why you do that. And the second thing you'll notice is that what you actually do is you have you don't just have one laser, you have two lasers from different ends of the baseline. And basically what they do is they do this kind of large momentum transfer. Basically, just the more laser pulses you do, the more momentum splitting you get between your two arms, and the bigger the space-time area enclosed here. And the bigger the space-time area enclosed, the bigger the sensitivity that you get. So you don't really need to know, but that's kind of what's going on there. And there are many of these, we call them very long baseline atom interferometers. So people do atom interferometry on tabletop, like it's been done a lot of time. Are there any atom interferometer people in the room? Just checking that I'm okay. Okay, so these are this kind of very long baseline is the idea that you've got these two things separated by, like, I don't know, like order 100 kilometer. Well, at the moment they're thinking about 10 meters, but you know, separated by some macroscopic distance. And the idea is that, so I should say that the atoms are in free fall. So you kind of shoot the atoms up, you do this pulses on them, and then you kind of let them freely evolve under gravity. So if you've got them separated by, if you've got these things in, like, I don't know, 100-meter drop tower, the amount of time that you can kind of perform these laser pulses increases, and your space-time area gets a lot bigger. So you get much greater sensitivity. So your sensitivity generically depends on, like, how far your baseline, so how long you're letting these things kind of travel, the time between, or the total time of your sequence, the total time you're interrogating these atoms. It depends on the number of laser pulses you fire, so we kind of call that n. And these systems are very clever. They can actually get down to shock noise limited sensitivity. So that means the sensitivity is entirely controlled by the number of atoms that you've got in your cloud. This is just your usual like Poisson statistics, like 1 over the square root of n. So that's the kind of quantum limit of what you can do unless you apply some kind of fancy entanglement or anything. So if you want to be able to sense dark matter with these things, with an atom interferometer, you need like your baseline to be about 1 kilometer long. And you also need to fire about 1,000 pulses. Okay, so that's quite stringent requirements. And as a result, if you want to be able to keep your atom kind of coherent for the timescales that are relevant, you need to operate on a ultra narrow transition. Okay, so you can't have your atoms decaying. If your atoms are decaying like while you're trying to do this thing, then obviously it's going to reduce the number of atoms in your cloud and increase your shot noise. So typically these atom interferometers are based on like strontium. So strontium is a clock. And because it's an optical clock, this means an atom interferometer can sense couplings to dark matter, coupling to photons, or coupling to electron masses. It can't do quarks or gluons, right? Because it's literally an optical transition. So there are there's kind of been a big proto collaboration of these atom interferometer people set up called TVBLAI, terrestrial very long baseline atom interferometry, I think. So there are various different things. They've got MAGIS, which is being built in Fermilab, so that's a 100-meter drop tower. There's already a 10-meter drop tower in Stanford. The VLBAI is in Hanover. That's again a 10-meter instrument, and AION have built a 10-meter one in Oxford. And the idea is to kind of, there's all these like little efforts at the moment, but the idea is that in the future, hopefully they'll be able to get like a 100-meter or a kilometer instrument that will be able to search for not only dark matter, but gravitational waves as well.
Just want to make sure I understand.
Yeah.
So it's like a standard QCD epsilon couples to photons. This is like an E.B coupling,
Yeah.
and or to
So we're not looking for E.B, we're looking for E squared minus B squared, which is a scalar coupling. So axions don't modulate energy levels at linear order because they couple like E.B as a pseudoscalar, but they do couple at loop level. So if at one loop level, and I'll show you a plot in a second actually, at one loop level, the QCD axion does cause these masses to oscillate. But the penalty is, of course, that it's quadratic in the axion field. Yeah. So you can absolutely use these to look for axions, but it's probably not going to be the best way of probing an axion.
But this is non-standard.
It's a scalar. So
instead of having a
pseudoscalar.
it's a scalar. Yeah.
Okay.
Yeah. Okay, so this is the current state of play. So these are 54 experiments. These are atomic clock comparisons. And this is what the nuclear atomic clock could do. So again, it's literally a forward of magnitude enhancement. And these lines are atom interferometers. So atom interferometers, what you can see is that it pushes your sensitivity region up to higher frequencies or higher masses. And it also generically improves the reach as well. This is if you could do it in space, but obviously, space is probably slightly far off at the moment, but this is kind of the terrestrial efforts that we expect. And yeah, so I should say that atom interferometers by themselves can only probe coupling to photons and electrons. You can't do couplings to gluons. So you can see that the constraint plot here is much more sparse. There's no atom interferometers here. So given that interferometers can do better than clocks, or can improve or extend or complement the reach of clocks, we had the slightly crazy idea of, if you could build a nuclear clock, could you then build a nuclear interferometer and do interferometry with this thing? So slightly pie in the sky, but I think given that the technology is out there and the rate of development that's really happening, now is the time to even think about this and potentially influence development. So it turns out that thorium-229 is not that great for doing an interferometry, and the reason for this is twofold. So to start with, if you have an atom, thorium-229, its atomic form, it's very unstable. So its lifetime is only 10 microseconds. So that means you're going to get a lot of spontaneous decay. So if you start with some big number of thorium atoms in your cloud, a lot of them are going to decay. And this puts an intrinsic kind of limit on the number of momentum transfers that you can do, and also your baseline length, because if you go above this, then everything will just decay and you won't get a signal. But of course, if you're working with something that's atomic, you can shoot loads of these things up. You can have like a big cloud of atoms, like 10 to the 6, 10 to the 8, 10 to the 10 atoms. So that's going to help with your statistics. Now, thorium-229, when I said, oh, they're going to use it for build a clock, you're probably thinking, well, if it's unstable, how can you build a clock? Well, it turns out it's not unstable if it's in an ionic form. So if you've removed the electrons, that actually removes the main decay channel. So therefore, if you've got just even thorium-229 plus or 2 plus or 3 plus, that actually becomes stable. So that means you can go to much longer baselines, much longer momentum transfers. You don't need to worry about things decaying. But the penalty, of course, is that an ion is charged. So you can't have a cloud of ions because they just repel each other. So that's going to kill your shot noise. So clearly atoms has a disadvantage in that, you're going to lose things to decay. Ions disadvantaged because you can't interrogate many of them at the same time. But the question is, the raw enhancement would be 10 to the 4. Do these problems overwhelm my 10 to the 4, 10 to the 4, 10 to the 5 enhancement that I would expect, or do they totally kill it? So I'm going to show you some estimates now. So actually, it turns out that given that the thorium is just so sensitive, that even with all these problems of working with it, you can actually beat sensitivity of normal atom interferometers. So this is just an example. If I work with atoms, I've got various different configurations with various different degrees of complexity. You can see that it's slightly able, it pushes the sensitivity reach out to higher masses. And it also is able to beat a typical nucleotrophic clock transition in this high frequency region. With a ion, you can get greater sensitivity, like peak sensitivity, but the improvement that you see at higher frequencies is less marginal. And that's for coupling to photons. But the kind of aim where this really comes in is the coupling to quarks or coupling to gluons or QCD. Because remember, typical atom interferometers don't have any sensitivity here. So actually, if you were to build one of these devices, you'd be able to probe a whole lot of uncharted parameter space. So I will say that, the caveat with this is it's far future. We don't have a nuclear clock yet. Being able to build a nuclear clock, then you need to be able to build an interferometer. So this is, future thinking. But it's just kind of being able to kind of scratch the surface of what we can do with these kind of technologies. And the question is, so someone asked about axions. So with axions, we can do the same thing. So actually the QCD axion coupling, it causes the pion mass to oscillate at quadratic order in the axion field. So that means thorium transition energy is also going to oscillate. And you can use these clocks and these interferometers to probe QCD axions as well. As you'll see here, the parameter space that you get is actually already ruled out by astrophysical constraints. So perhaps less motivated for this case. But certainly it will provide an independent laboratory test in a controlled environment should you build this experiment. Okay, so I think that's all I'm going to talk about scalar dark matter and pseudoscalar dark matter. Does anyone have any questions on any of that? Yes.
It's more just what the experimental pathway might be here. So I don't know everything about it, but the current thorium transition work that's being done, the thorium's implanted in crystals, if I'm not mistaken. So this would have to be in a regime where you get it out of the crystal.
Yes, so there are two types of thorium clock which are being potentially developed. So the initial kind of work on spectroscopy is being done in a crystal. And the idea is that, yes, they would try and build a solid state thorium clock, but they're also talking about building single doubly charged ion clocks. So the idea is once at the moment, the reason they're working with crystals at the moment is they don't really know the transition energy. So if you've got lots of atoms, then you've got more chance of exciting them, etc. So that's why they're working with crystals at the moment. But the hope is eventually when they actually build thorium into a timepiece, it will be in a single ion clock. So you have a single ion in a trap and you excite that. So these two different realizations, one is just working with clouds of thorium-229, like atoms. So again, that's unstable. That wouldn't be suitable for a clock, but it turns out it could be used for interferometry with the penalty of that. And then this one would be just dealing with a single ion. So it would be just taking a single ion clock, but putting it in free form. So you'd have it trapped, you'd then like release it from the trap, do the interferometry, and then trap it again and then repeat. So yeah, very good question. I mean, if you could do this kind of interferometry in a crystal, or perhaps if you could dope this into a molecule, that'd be even better. But I don't know enough about kind of molecular science to know whether you could do that. The advantage of doing it in a molecule would be that it will be neutral, but perhaps also stable as well. So that would allow you to kind of bypass both of the problems that we have with these systems. Okay, yes.
If one is just interested in fuzzy dark matter from an astrophysics point of view, does this make sense for dark halos and so forth, cosmology? How generic are these couplings? I mean, you're sort of adding something new to the model that isn't necessary at all for astrophysics, right? You could just have fuzzy dark matter that just interacts gravitationally.
Doesn't act gravitationally yet.
But you're ruling out a particular class.
I'm ruling out anything. So if you have fuzzy dark matter, and it's going to be a scalar or a pseudoscalar or a vector. So by the law of EFT, you'd expect generically these things to couple to the standard model. And whenever you do a particle physics experiment, you're always looking at this coupling. So this is what direct detection is. Of course, it's not generic, but it has to. But it has the right symmetries to be able to do this. So if you have a scalar particle, these couplings, they might be very small, but you would generically expect there to perhaps be some coupling. So yeah, you're right that it doesn't need to be there, and it may be that dark matter doesn't have any non-gravitational coupling, in which case any kind of direct detection experiment is not going to work. You need to use, gravitational waves astronomy. But I think I like to be an optimist, and I think, it would be nice if we were able to probe dark matter in the lab. And in that case, yes, you would expect there to be some coupling. It's no different to people saying, oh, you have like some axion-like particle that couples to E dot B. It's the same kind of philosophy that, that coupling could be there.
Right, but in that case,
you have
written down a Lagrangian, for the QCD axion that's motivated. So in this case, if people are trying to write down actual models of a 10⁻20 electron volt.
Yeah.
Well, I mean, how far along has that?
Yeah. Okay. So there is an issue. So the QCD axion, I agree that its coupling, its fundamental coupling to gluons is motivated because we need it to solve the strong CP problem. But people also think about ALPS, where they just say, okay, well, it's just a generic coupling. So this is much in the same philosophy. The issue, the one issue with scalars as opposed to pseudoscalars is that the couplings, if you add these couplings, it generically induces like mass corrections. So there are kind of naturalness fine-tuning issues with light scalar models which don't exist with axions. There are ways of getting around it, like with kind of SUSY. So if you have like a light pseudoscalar that has a SUSY partner that's a scalar, then if your pseudoscalar is light, then your scalar is light. So there are kind of constructions, and people are working on this. There does need to be more work, but I think from a kind of detection point of view, it's really thinking about an effective field theory level. What are the possible couplings there, and what signatures are there? These devices, clocks and things out there are already being built for like GPS and all sorts of other different reasons. So it's all just thinking about given that these technologies are out there, what could you do with it, and what sort of dark matter models would you be able to do? Cool. Okay. Great. So in the last sort of 10 minutes or so, I'm just going to switch track and introduce you to a different kind of dark matter. So again, we were talking about scalars and to some extent pseudoscalars. Now I'm going to talk about vectors or spin one. So you've probably all heard of the dark photon. The dark photon, which is something which just interacts with the standard model via kinetic mixing. That's why it's dark. But alternatively, if you've got a spin one vector boson, it can actually interact via a direct gauge coupling to the standard model. So in this case, you've got some additional U1 symmetry that you've gauged in your theory. And that means you've got a preserved or a conserved quantity, in this case, baryon minus lepton number. And you can write down your Lagrangian. And you have this coupling, which is basically just coupling your dark spin 1 particle to this thing here, which is basically just neutron number. And it turns out that this thing actually induces a force on macroscopic objects. So this is exactly in the same way that you derive the Lorentz force in electromagnetism. You can derive a force acting on this thing, and it depends on the number of neutrons in your macroscopic object. So this gives you a very distinct signal, because if you've got 2 different masses, and your 2 different masses have different neutron to nucleon numbers or neutron to proton numbers equivalently, you're going to get a differential acceleration between them. Okay, so you can actually measure like a positional shift between 2 objects with different neutron to proton numbers. So how can we search for this? Well, the kind of name of the game here is optomechanical sensors. So an optomechanical sensor is literally just a harmonic oscillator, but it's a harmonic oscillator that you couple to an optical field, so just a laser, and that optical field is used to read out its position. So you can imagine you've got something in a trap, it's just oscillating. If your dark matter comes in, it's going to change that oscillation. You can read out the position very precisely, and that allows you to sense whether there's been an external force acting on your object. So again, there's been a kind of bewildering array of developments in these optomechanical sensors over the last kind of 10, 20 years. And there's many different types. Historically, people have focused on kind of suspended cavity. So this is basically just, you've got like a pendulum on a string, and you're reading out the position of that pendulum with a laser. They're great. They've been very well studied. Unfortunately, if you can imagine, the mechanical frequency of your pendulum depends on the length of the pendulum. So you can't really, it's quite difficult to tune the frequency, your mechanical frequency of your pendulum. So that's one disadvantage of that. And then more recently, within the kind of last 10 years, there's been a huge development of levitated systems. So this is where you use either an optical, magnetic, or some combination thereof of fields to actually trap a particle so that it's suspended or levitated. And the big advantage of this is it's more isolated from your environment. But it works in the same way in that you've got some suspended thing and you're measuring its position using an optical field. Now, much in the same way that atom interferometers were controlled by shot noise, you've got 2 sources of quantum noise that affect these mechanical systems. You've got kind of shot noise, and you've also got back action noise. And these things kind of trade off. If you can imagine your laser that you're using to read out the motion of this thing, the more photons that you put in, the more statistics you can do. So the more precise your readout is. But also, the more photons that you have scattering, the more recoil you're going to get, and the more noisy that you're going to get there. So when people do these searches, you want to get to the sweet spot. So the sweet spot is that the power at which the sum of these things is at its minimum. And it turns out this is when the shot noise and the back action are equal. Okay, that's just quantum mechanics. And this is known as the standard quantum limit. In fact, it's a bit like it's an exact analogy of the Heisenberg uncertainty principle. You can only know the position and the momentum so well. This is exactly the same thing. You can only get the noise to a certain level unless you apply kind of squeezing techniques or anything like that. But this is the idea here, is that you always want to get to the standard quantum limit, and people have been able to achieve this already in the lab. And what it requires doing is choosing your power to the exact sweet spot at which these 2 things are equal. Okay, so we're going to focus particularly on optically trapped systems. And the reason for that is because, as I said, they're isolated from the environment. They're a development that's it's very new, and they've yet to be kind of really studied for dark matter detection. So the deal with an optically trapped system is you've got a laser, and you're using that laser to trap an object, and you're using the same laser to read off the position. So this leads to some subtleties, specifically that the mechanical frequency that your thing is oscillating at then depends on the laser power. And this has some significant implications for noise minimization, which weren't realized before kind of this work, which is that your mechanical frequency depends on the laser power. So you can't just tune the power to get to SQL without changing, taking yourself away from resonance. So you need to be a little bit careful about that. But more to the point, it turns out that the noises of these systems depends on the size of the system that you're levitating relative to the light. So if you've got a very, very small object, so the dimensions of your sensor are much smaller than the light, it turns out that your best noise that you can get scales exactly in the same way as your sensor mass as your dark matter signal. And this is kind of fundamentally limiting because dark matter signal scales with mass. So you might naively think, well, okay, well, if I just levitate a larger sensor, I'll get a lot better sensitivity. But this is saying, well, no, because if you increase the mass of your system, the noise is going to increase in the same way, and you're kind of screwed. And this is the regime that people have really studied. So up until now, people have only really been levitating these nanoparticles. That's kind of where the bulk of work has been done. But it turns out that if you can build a significantly large sensor, and that sensor is now sizable compared to the wavelength of your field, the SQL noise is scaling far less deeply than the dark matter signal, okay? And the reason for this is all to do with the way that this object is scattering light. So this is behaving as like a dielectric emitter, and this is now behaving like ray optics. And because of this change in scaling, it's beneficial because it means that you're able to, if you can levitate something that's larger, you're going to get a better signal to noise ratio. So this is kind of really motivating work in this region. But as I mentioned, people have never really explored this before. There doesn't exist the infrastructure to be able to kind of levitate these objects. So that was kind of the point of this work. And this is where this proposal enters. It's called Molecute, which is a massive optically levitated quantum tabletop experiment. Not my idea, I can't take credit for that. But basically, it's a design of an optically trapped system which is able to levitate a high mass object in the geometric optics regime. And that means you're able to really benefit from this enhancement as you get to higher masses. So here we're talking about levitating, milligrams or grams with lasers. So you've just got some like kind of silicon wafer here covered in a high reflectivity coating, which prevents it from melting. These horizontal beams are what causes the oscillator potential, but because it's so heavy, you also need a kind of vertical beam to support its weight. And the nice thing about this design, unlike the nuclear interferometer, is this is entirely technology which is achievable in the labs. We're working with some experimentalists at the moment who are hoping to try and build a prototype of this experiment. So it is, the power requirements, the requirements on your vacuum chamber, things like that, is all things which are kind of standard in these mechanical labs. And I should mention that you're measuring the relative displacement of your sensor from the optical table that it's on, because remember, you're always looking for differential acceleration. So just to show you the kind of sensitivity plots that we've got. So again, these are kind of the standard fifth force tests. You can see that even with the smaller mass, which is like a kind of very feasible thing, you can get like half an order of magnitude improvement in sensitivity, whereas you can get over 2 orders of magnitude if you could get up to a higher mass. And again, this is all assuming very modest resource integration times and etc. And I think it's actually really cool that, so LIGO, the way that they're using this for B-L dark matter, LIGO is basically literally just suspended mirrors. And that is a huge mass. So you might think, well, why are you able to do better with just doing a tabletop experiment is nothing like LIGO. And it's really because LIGO is looking at the gradient of the field, right? It's looking at the differential measurement of these two, of the force, right? Whereas we're measuring the force directly. And this really, to me, shows that LIGO, of course, was not invented for B-L dark matter, but this is really motivating why you need targeted experiments, where you need to work with experimentalists and actually think about why or how you can target your experiment to search for different things. So this was a design of this design is really developed from first principles to be able to search for these classes of dark matter. Okay, I'm going to shut up now because I've been blabbing on for too long. But I just want to kind of really get across that there's been huge amounts of development in these quantum sensing technologies over the last kind of 10, 20 years. A lot of the opportunities have been not explored for dark matter at all. I've just shown you some very naive examples of what you can do. They might not be the most well-motivated models for new physics, but I know there's a lot of you doing really cool science out there, and you've got different ideas. Maybe you're working with neutrinos, maybe you're working with cosmic rays, maybe you've got ideas that could harness these technologies. If you do, I'd love to hear it, because I reckon there's a lot more that could be done, but we really need people to get together and talk. and think about kind of the way forward for these things. So thank you very much for putting up with me for the last hour. And if you have any questions, please let me know, and I'd be really happy to chat with anyone at any point over the next couple of days. Thank you.